In this course, I thought let me include few additional topics. They may not be corresponding directly to the material and heat balance in metal extraction, but they do involve a material and heat balance. So, in the series of additional topics, the first which I have thought is the melting in cupola. There will be other additional topics that I will introduce to you in the next few lectures. So, the first topic additional which I have thought is melting in cupola, because as all of you know, pig iron when it is produced from blast furnace in the cast form is not useful at all. In the foundry, the pig iron is melted in order to produce castings of cast iron. So, in fact, if we say cupola is used to produce castings of cast iron in foundry. In construction, it is not like blast furnace as that tall, because it just required to melt, no reduction is going on. So, as such the diagram which I have shown here is a schematic diagram of a cupola. Now, in the cupola, this region is called stack, this is called stack, and from the periphery of the cupola air blast is introduced. Air blast is introduced. This is also air blast. Now, its operation is very simple. The burden which is charged from the top it consists of pig iron plus coke and to some extent limestone is also used. So, this burden which consists of pig iron, coke and limestone, it descends downward, and as the combustion occurs between coke and blast of air, the gases which are shown by the red color, since we are introducing nitrogen and carbon of coke will combust. So, the gases will comprise of CO, CO2 and nitrogen also. So, they travel upwards, and there is a heat transfer and to little extent mass transfer may occur between the descending charge and ascending hot gases. On the hearth, so this portion is a hearth where the metal which is the liquid which is usually cast iron is collected at the bottom and slag is disposed. This is the outlet for slag and this is the outlet of metal. This is a very simple operation of a cupola. Now, I will just for your information I will note down few points. Say one, the burden it consists of say pig iron plus scrap. I can also include here to some extent you have scrap also here, scrap plus coke and plus limestone. This is the burden. It depends, if the scrap is there you can charge, because there is no problem in operation of the cupola, because the source of energy is from outside. So, there is no problem, you can, if the scrap is there you can charge, if not there you can work with the pig iron also and get it refined. So, source of energy, rather source of thermal energy is combustion of coke. You know, combustion of coke, it generates a very large amount of energy. When carbon combines with oxygen from CO2 and CO, a very large amount of energy is released. So, this is the source of energy, and now operation, just few points. First of all, it is simply a melting unit. As such, it just melts pig iron and scrap and to produce a cast iron of certain composition. Now, since coke and limestone are being added, so that means there are some purpose for which coke and limestone is added. So, as a result of combustion of coke and blowing of oxygen, there are some oxidizing conditions. So, during the operation, point number 2, some oxidation of silicon, manganese and iron occurs, and as a result of the oxidation of silicon, manganese and iron, you get SiO2, MnO and FeO. Carbon may also oxidize. Carbon may also oxidize. So, as a result of oxidation of carbon, some carbon may become lower, but then because the coke is there and carbon is there. So, the whatever amount of carbon which is oxidized, the carbon gets absorbed from the coke and we get to the specification. So, the oxidation of silicon, manganese and iron, they are to be controlled so that no additional charge of silicon, manganese or iron is required in order to meet the specification. Carbon, well, if it is oxidized, there is no problem, but then it gets absorbed from the coke carbon. Another say important thing is that it is not a continuous operation, because it depends on the demand. In fact, you are producing the cast iron castings, you have to have so many operations to be ready before you run the cupola. One of the operation is that mold should be ready. Another, there should be sufficient market to sell that particular cast iron. As a result of this, the cupola, it runs intermittently. So, that is what in short the various points of cupola, and in fact, the last point which I would like to mention, the slag which will form, it may contain SiO2, MnO, FeO, and because in order to flux this particular slag or in order to remove this slag, and in order that these components be liquid at the temperature of inside the cupola, you add some calcium carbonate. So, that calcium oxide helps to form the slag and it slagged off all the impurities. It may contain sometimes some amount of calcium oxide. So, that is what in short the operation of the cupola is there. Now, the further operation what I have thought I will illustrate through the problems on material balance in cupola. So, let me go to the material balance in cupola. So, now I will see that there are certain few problems I have selected. So, to illustrate more the operation of the cupola, and here is the first problem. Note some correction is there, instead of 26 there is 22 kg is used. So, pig iron and coke are charged in a cupola to produce an iron casting. The flux is pure calcium carbonate. Now, it does not matter because you are supplying extra amount of energy. So, calcium carbonate may decompose to CaO and CO2, and all of you know through the earlier lecture that calcium carbonate decomposition is highly endothermic. So, it does not matter because you are supplying now the source of energy from outside. It is not the process or the cupola melting is not in a sense autogeneous. So, you should worry for that. used say 22 kg is used per ton of pig iron, the coke used is 125 kg per ton of pig iron, the composition of coke is also given over here, 85% carbon, 6% SiO2 and so on. The gas from cupola contains CO is to CO2 ratio as 1:1 by volume. No carbon is oxidized from pig iron. The slag from cupola, its composition is given. It has FeO, SiO2, MnO, CaO and L2O3. The cast iron produced carries 3.8% carbon besides some manganese and silicon. Let me have some correction over here. So, this is not sulfur, this is in fact silicon. So, it has some silicon. Now, what is required per ton of pig iron? You have to produce, you have to calculate weight of slag, volume of air consumed in oxidation of carbon of coke and volume and percentage composition of gas. These are the things you have to calculate. Now, here is the second problem, and second problem says a cupola melts per hour 15 tons of pig iron of composition carbon 3.5%, silicon 2.2%, manganese and phosphorus, the composition is given, and 5 tons of scrap containing, this is the composition of scrap. Now, note, as I said in the burden, pig iron plus coke plus scrap and calcium carbonate. Now, well, you are seeing here that pig iron is one component of the burden, another is the scrap, the two, and the third is also coke, and fourth is the limestone. The dry air used is 849.6 meter cube, measured at 313 Kelvin to melt 1 ton of pig iron in scrap per minute. So, you should know, you should read the problem very carefully to solve this problem. During melting, 20% of total silicon charged, 15% of total manganese charged, 1% of total iron charged and 5% of total carbon is oxidized. 19% of carbon of coke is absorbed by iron during melting. Enough calcium carbonate is charged to give 30% calcium oxide. So, you are seeing the component of the burden, as I mentioned in my introductory remark, pig iron, scrap, limestone and coke. We are meeting all these over here. The coke is 92% carbon and 8% SiO2, somewhat better quality coke than the problem number 1. And weight of coke is 1/9 of the total weight of pig iron and scrap. To calculate charge balance of cupola for 5-hour run. Now, in order to calculate charge balance, you have to know what charge balance means. That means input and output. Now, nobody will tell you what are the inputs and what are the output, but still the problem demands that the total charge balance should be there, whatever is input should also be the output. That means, you have to think what consists of the balance and the percentage composition of resulting cast iron, slag and gases. So, here these are the two problems. Now, let us proceed to the solution of these problems. So, here we go for the solution of these problems. So, let us take the solutions. Say problem number 1, and let me represent the problem as a block diagram. So, as the input we have pig iron, then coke, and coke amount is 125 kg per ton of pig iron, and flux we are having 22 kg again per ton of pig iron. Of course, composition is given. Then in the output we have CO is to CO2 ratio is given to us 1:1. Then it is also given in the output slag, and the slag contains FeO, SiO2, MnO, CaO and L2O3. Then we have cast iron, and it is said that in the cast iron carbon is 3.8%. It contains manganese and silicon. No percentage of manganese and silicon in cast iron is given. So, you cannot find out what is the percentage iron at the moment. Slag, well, composition you can, if you wish you can write down 12, 45, 3, 25 and 15. So, that is now we are required first of all to calculate weight of slag. So, first let us calculate weight of slag. Now, clue to calculate the weight of slag, जिसको हिंदी में बोलते हैं गुरु मंत्र, is to find out a compound which exclusively enters into the slag. Now, if you see this particular problem, you note that the Al2O3 which is present in the coke, it directly enters into the slag. Also, calcium carbonate which decomposes to calcium oxide in CO2, CaO directly enters into the slag. So, you have an option whether you go for Al2O3 or calcium oxide. I will see for both the options. So, if we take set, say X is the amount of slag, X is amount of slag. Let me do first of all Al2O3 balance, Al2O3 balance, and of course, the basis I am taking 1000 kg pig iron. Let me write down, basis is calculation is 1000 kg pig iron, that is my basis of calculation. So, if I do the Al2O3 balance, well, then I can immediately calculate X, that is equal to 125 into 6 upon 100 into 0.15, that is the 15% Al2O3 in the slag. So, this immediately I get the amount of slag is 50 kg. Immediately it turns out to be amount of slag is 50 kg. Now, what I thought, let us calculate by having calcium oxide balance. I mean, both should give the same answer. However, you can choose any, because the guru mantra जो है वो ये है कि find out that component in the overall problem which directly enters into slag. Suppose if you select SiO2, you may end up in the problem because part of the silicon is entering into pig iron also, and that is not given. So, you cannot do any SiO2 balance. Similarly, manganese oxide you cannot do MnO balance. FeO you also cannot do the FeO, iron balance you cannot do it, it is not possible, because all the requirement of the variables that are not available. So, even if you select silicon as a balance, then you are end up in a problem. So, here Al2O3 and calcium oxide, they are the oxides which directly enters into slag. Even if you have among Al2O3 and calcium oxide, because if sometimes sulfur is present, then calcium oxide reacts with sulfur and forms calcium sulfide, you may end up in the problem. But the Al2O3 is such a oxide which is very friendly in the sense it always enters all of it into the slag from all the sources, no reaction, nothing happens. So, Al2O3 balance should be the key to arrive at the weight of slag by balancing it. So, that is what I thought I will tell you. So, if you do for example, calcium oxide balance and if we calculate X, that is the amount of slag, so that will come out to be equal to 49.28 kg. So, you see both values are quite close for as regard the 50 kg. So, we take 50 kg is the correct answer. Now, second part B, you are required to calculate volume of air, required to calculate volume of air in oxidizing silicon, manganese and iron. Now, we can calculate the volume of air in oxidizing silicon, manganese and iron, because what happens, say during melting of pig iron, some oxidation of the element that take place. Now, what are the reactions? Say silicon in pig iron, it reacts with oxygen, gaseous form, and it gives you SiO2 as slag. Similarly, manganese in pig iron reacts with half O2, gives you MnO in slag, and iron of pig iron plus half O2 gas, it gives you FeO. These are the oxidizing reaction where oxygen of the air is used. There is no other source of oxygen. The decomposition of calcium carbonate could be, but it provides CO2. Now, say if you want to calculate say SiO2 due to oxidation of silicon of pig iron, due to oxidation of silicon of pig iron. Now, first of all you have to find out how much silicon content is over there. So, that will be equal to say SiO2 from charge, SiO2 from charge minus SiO2 in slag. We know both the quantities. So, we can calculate SiO2 from charge. You have to calculate now, to consider now from all sources from where SiO2 is entering, and SiO2 in slag is already given. You have found out the amount of slag. So, you can find out that quantity. So, this quantity comes around say 15 kg, and this is equal to 0.25 kg mole of silicon gets oxidized. So, oxygen required would be O2 required would be how much? As the result of this reaction, 1 mole silicon, 1 mole oxygen. So, 0.25 mole, you require 0.25 moles of oxygen, 0.25 moles of oxygen will be required. On a similarly, one can also calculate manganese and iron oxidation. Similarly, one can also calculate manganese and iron oxidation, because you know FeO content of slag, you know MnO content of slag, and from that you can calculate. So, oxygen for MnO oxidation, you can calculate, I am giving you the values, that is equal to 0.011 kg moles, and O2 for iron oxidation, that comes out to be equal to 0.0156 kg moles. So, now there is no problem. Volume of air as required in the problem, that will be equal to what? That will be equal to say 0.25 plus 0.011 plus 0.00 plus let me say plus 0.0156. If you divide it by 0.21 multiply by 22.4. So, volume of air will be say 29.5 meter cube at 1 atmosphere and 273 Kelvin. So, that is what the answer for this. Now, the next which is asked C, say volume of air for carbon oxidation, Now, here again the clue to solve this particular problem. First is that it is oxygen of air blast, it reacts with carbon of coke. That means, something you have to think in terms of to find out oxygen of the air blast, because that reacts with the carbon of the coke. Another thing is that CO-CO2 ratio in the top gas. Now, you have to think that CO-CO2 ratio in the top gas will comprise of what? It comprises of oxygen of the blast as well as oxygen which you are getting from reduction of SiO2, MnO and so on. You are also getting oxygen from calcium carbonate. Also carbon you are getting from calcium carbonate. So, these are the various things that you have to consider while calculating the volume of air for carbon oxidation. So, now the condition, the problem says following, problem says no oxidation of carbon or pig iron. So, it becomes little simple, no oxidation of carbon of pig iron. The problem also says that the exit gas CO is to CO2 ratio, that is equal to 1:1. So, we have got a clue. What I am going to do? We have to do carbon and oxygen balance. So, let us take the y kg moles CO and CO2. Therefore, y by 2 kg mole CO and y by 2 kg mole CO2. Now, we have to do carbon balance. You have to do first of all carbon balance. See that from all sources, from wherever carbon enters, the carbon of the coke, carbon of calcium carbonate, and it exits carbon in cast iron and so on, and you have to do all this balance, and the balance will result this particular equation 8.854 plus 0.26, that will be equal to y by 2 carbon in CO and y by 2 carbon in CO2, y by 2 carbon in CO and y by 2 carbon in CO2. There is no need to write. This is our equation number 1. Now, let us write down second is the oxygen balance. Second is the oxygen balance, and let us take that Z kg moles oxygen derived from air. Again here you have to do oxygen balance. So, this will give you Z plus 0.411, that is equal to 0.75 y. Say y by 2 moles in CO2 and y by 4 moles in CO. So, this is my equation 2. Now, we can solve equation 1 and 2. So, by solving equation 1 and 2, I will be getting say y, that is equal to 9.114 and Z, that is equal to 6.4245 kg moles. So, I can immediately find out volume of air. In that 6.4245 divided by 0.21 multiplied by 22.4, this will be equal to 685.3 meter cube. That is the answer for this particular problem. Now, next I have to calculate volume and composition of gases and composition of gases. Now, volume already we can calculate now, that is CO, it is half of 9.114, that is 4.557, CO2 same 557, and nitrogen, that will be 25.196 all in kg moles. So, that will be 13.28, 13.28 and 73.44, they are all in percentage, where this is in kg moles. Now, say volume, it is easy to find out. Volume of gases, that will be 765 meter cube. Now, let us go to the second problem. Now, in the second problem, say given, it is given to us, well, it is important that you read the second problem carefully. the charge of 15 tons of pig iron and 5 tons of scrap, they are given per hour, but the blast rate is given per minute. So, that point it should be clear. One. Number 2, the blast rate is given at 313 Kelvin. So, I did some conversion and that conversion you should also do it. So, in that I will write now given in terms of per minute. You can also calculate in terms of per hour, the choice is up to you, but then whether you calculate per minute or you calculate on the basis of per hour, it should be consistent. So, what I have done, I am calculating now per hour. So, per hour charge is 333.3 kg per minute. With charge I mean it has pig iron plus scrap. That is what the charge is per minute. Coke also I have to calculate per minute. Coke per minute, that is 37 kg per minute. Then I have to calculate oxygen in blast, and oxygen in blast, that is 2.32 kg moles, and nitrogen in blast, that is equal to 8.72 kg moles. Now, these both I have written on per minute basis, and also the volume flow rate which was given at 313 Kelvin I converted, and these values are at 1 atmosphere and 273 Kelvin. So, you can choose the basis way you like, you can calculate on per hour basis or 2 hour basis, whatever you do. It is only the thing what I wanted to tell is that you should be consistent in your calculation. Now, what you have to calculate? We have to calculate charge balance. We have to calculate charge balance. You have to calculate charge balance. You have to calculate charge balance, and charge balance comprise of, when we talk of balance, input and output. That means, in this particular problem, it is not specifically asked what you should calculate, only asked make a charge balance. That means, your balance should be complete. No quantity should be missing in the input and output side. So, if you see the problem, what is say, it is the amount of calcium carbonate is to be calculated. Then you are also required to calculate slag amount, that is also not known. So, here I mean this type of calculation tells you whether you understand the material balance of cupola or not. Here it is not specifically asked what you should calculate, what you should not calculate, but then you should still calculate completely, so that input and output they match each other. So, slag amount is also not known. Exit gas volume is also not known. Exit gas volume is also not known. Then weight of cast iron is also not known, or say amount of cast iron is also not known. So, these are the quantities that you have to calculate. Now, say calcium carbonate amount we cannot calculate unless we calculate the slag amount. So, our first thing is that we have to calculate amount of slag. Let us calculate first amount of slag. Now, here you are not given any percentage or nothing you are given. You have to read the problem and see, do the balance and see what is happening to what element. So, seeing the problem and looking into the introductory remark of my lecture on cupola melting, the slag will consist of, in this situation, will consist of SiO2, MnO and FeO. So, we have to calculate now. So, SiO2 in slag, SiO2 in slag, that will be equal to SiO2 of coke, because whatever SiO2 which is present in the coke, it will go to slag, plus Si of pig iron oxidized to SiO2. And there is no other source from where SiO2 is entering in the slag. So, if we calculate all these things, we get SiO2 in slag, that will come out to be 5.96 kg. So, in doing this type of balance, you should be very cautious that you do not forget any source from where SiO2 is entering in the problem and you have forgotten to calculate or to consider. So, that way the problem reading in between the lines is very important, and little bit of knowledge of the operation of the cupola, say physicochemistry of the cupola, what is oxidized and what is not oxidized, that is also necessary. So, SiO2 in slag is this one. Similarly, we can find out say MnO, because the source of MnO is only oxidation of manganese and there is no other source. So, that will be equal to 0.57 kg. Similarly, one can calculate amount of FeO, that will be 4.00 kg. So, in addition to the amount of slag which I wrote SiO2, MnO and FeO, it will also contain calcium oxide, because if you read the problem says that the slag contains 30% of calcium oxide. So, now if you consider X is the amount of slag, say if you consider X being the amount of slag, X is the amount of slag, then 70% consists of SiO2, MnO and FeO, because 30% is calcium oxide. So, if we sum total and divide by 0.7, then we get amount of slag, we get amount of slag that is equal to 15 kg per minute. Now, once we get amount of slag equal to 15 kg per minute, then we can calculate amount of calcium carbonate. Amount of calcium carbonate, because 30% calcium oxide in the slag. So, 15 into 30 by 100, that will be calcium oxide, convert to calcium carbonate. So, this will be equal to 8.04 kg per minute. This is about the amount of slag and amount of calcium carbonate. Now, we are also not given what is the volume of exit gas. So, we have to calculate now the volume of exit gas. To calculate volume of exit gas. Now, we adopt the same procedure as we adopted in the earlier problem. Here, let us consider now say x kg mole CO2, x kg mole CO and y kg mole CO2, y kg mole CO2. So, let us do first of all carbon balance. So, carbon balance. Now, carbon balance, say write down, say carbon from coke, carbon from coke plus carbon from CaCO3 plus carbon from scrap plus carbon oxidized from pig iron in fact, also carbon oxidized from scrap. Whatever oxidation, all will be in the exit gas. The total carbon balance has to be there. So, that will be equal to carbon in gases, because that amount of carbon will not enter into the gases which has dissolved into the pig iron. Rest from all sources, because input should be equal to output. So, this is about the carbon balance. Now, similarly, we have to do the oxygen balance. So, I am performing oxygen balance, and this oxygen balance is, say, oxygen from blast, oxygen from blast plus oxygen from calcium carbonate, that is equal to oxygen in gases, oxygen in gases. Now, I will just write down in terms of the equation. So, the equation becomes x plus 2y, that is equal to 4.72, and this is our equation number 2. Now, by solving equation 1 and 2, by solving equation 1 and 2, you know, they are simultaneous equations, two equations, two variables, it can be solved. So, by solving equations 1 and 2, we get x, that is equal to 1.1268 kg moles, and y, that is equal to 1.7966 kg moles. Now, the exit gas comprises of carbon monoxide, carbon dioxide, and of course, nitrogen, because air is used for blowing purposes. So, first I will write in kg moles. So, carbon monoxide is 1.1268, CO2 1.7966, and nitrogen 8.7232, and in percent this becomes 9.67, 15.43, and 74.90. So, now we can calculate total amount of exit gas. Of course, we have to sum total, and that will be equal to 11.6466 kg moles per minute, and this becomes, that is equal to 260.88 meter cube per minute. So, that is what the question which was asked. Now, we can also calculate the amount of cast iron. Amount of cast iron. Now, we have to calculate the amount of each individual elements in cast iron, and all of you know it comprises of carbon, silicon, manganese, phosphorus, carbon, and of course iron. So, the amount is, say I will write iron, silicon, manganese, phosphorus and carbon, and their amount in kg. Say iron is 307.10, silicon 5.60, manganese 2.48, phosphorus 1.92 and carbon 12.19, and this makes total, that is total weight of cast iron 329.29, and we can also calculate in percent. So, in percent it becomes 93.26 iron, 1.70 silicon, 0.75% manganese, 0.58% phosphorus and 3.71% carbon, and this makes total as 100%. Now, it is also being asked what is the charge balance for 5-hour operation. So, I am making now charge balance for 5-hour operation. That means, if suppose the cupola operates for 5 hours, how much charge we have to keep in reserve. So, this can be calculated. So, we will be needing pig iron, that we will require 75 tons, scrap 25 tons, then blast, that is air blast, that will be requiring 22.23 into 10 to the power 6 meter cube, which is measured at 1 atmospheric pressure and 273 Kelvin. Coke, we will be needing 11.1 tons, and calcium carbonate, that will be equal to 2.41. Now, as a result of 5-hour operation, the output we have to calculate also, so that we can schedule our entire operation after tapping cast iron from the cupola. So, the slag will be produced, so amount of slag, that will be equal to 4.5 tons. Cast iron, that will be equal to 98.8 tons, and gases, that will be produced 23.48 into 10 to the power 6 meter cube, measured at 1 atmosphere pressure and 273 Kelvin. Now, this is very important to express pressure and temperature whenever you want to express the volume of the gas. If you want to calculate a 298 Kelvin or any other temperature, then this volume will not be same.